Okay, here I am with a calculator's OK page. I've got a pretty standard solve for x with x being in the exponent, so that's really a tip-off that you're going to need to use logarithms. First thing you do is you want to isolate that 3x minus 2, which is difficult to see now, but I'll write it bigger in a second. I just add 4 to both sides, and by doing that then I get 7 times 5 to the 3x minus 2. That's going to equal 700. Well, then I divide both sides by 7, and I get 5 to the 3x minus 2 equals 100. Okay, here resist the temptation to divide both sides by 5. That is an exponent with a variable, so I've got to use logarithms. Okay, so hit it with a great big log right here, both sides, and that is going to then become log, that'll be base 10 of 5, and then this will come out front. Okay, well, I'm just going to actually write it as multiplication at the back here to save room, 3x minus 2, but you can imagine it being multiplied out front. It's no big deal. Well, log base 10 of 100 is just 2. So now I'm going to divide both sides by log base 5, so I get 3x minus 2 is going to be equal to 2 over log base 10 of 5, and then I'm just going to add 2 to both sides. That will get rid of that, and I'm going to divide both sides by 3. So x then is going to be equal to 2 divided by the log of 5 plus 2, then the whole thing times 1/3 or divided by 3. If you do that, you're going to see that x is very close to approximately 1.62. All right, 620, I think, if you round. So there's the answer to that one. Next one is you've got this population of these little Daphnia critters, and they're tripling, not doubling, every 5 days. So you can write a simple equation, and that would be that the population based on t days is going to be given by the initial starting amount, 150, times 3 times t over 5. This is our way of accounting for that tripling period or doubling period or half-life of whatever it is. That's our equation. And then when will 3,000 of those critters be present? Well, you just write 3,000 is going to be equal to 150 times 3 to the t over 5. Okay, if I divide both sides by 150, I get 20, and that's going to be equal to 3 to the t over 5. I can then take the ln of both sides or whatever. If I do ln here and ln there, I get ln of 20 is going to be equal to, when this comes out front, t over 5 times ln of 3. Divide both sides by ln of 3. I get ln of 20 over ln of 3, and then I might as well just multiply both sides by 5 times 5, and that equals t. All right, and if you do that math, you're going to see that t is approximately 13.634. Okay, you can grab a calculator and verify that. You just want to type it in very carefully, divide that log by that log, multiply by 5. A nice thing about these is you can quite easily plug them in with your calculator and verify that they come out really close. Okay, you're not going to be bothered if it comes out to 299.9, because that's part of our round off error. Okay, I hope that wasn't chopped off with the camera, but there we go if I wasn't showing it before. Okay, so now here I've got an inverse that I'm going to find of this function. So our steps are that I first replace f of x with y, and that's going to be ln of x plus 2 minus 3, and then I switch x and y, so I have x equals ln of y plus 2 minus 3. Now I just want to solve and get it to be y alone by itself. So I add 3 to both sides, so I get x plus 3 equals ln of y plus 2. And I kind of like doing this from left to right, so I'm going to write it over here again. If I take this, well, then I can remember that this is base e, and if I just bring this over with my arrow rule, I can write y plus 2 is equal to e raised to the x plus 3. Again, this is just our definition of what logarithm is. it's written out of logarithmic form into exponential form like this. So then this part of it I can write over here as just y equals e to the x plus 3 and then minus 2, and then that will be what I can write as my inverse function, f to the minus 1 of x. Okay, so there it is. This final one, I think that it says sketch the graph. So if you go on your calculator and plop that in and are careful about the window, you'll see it's relatively straightforward. It's going to give you an upside down quadratic. You know it's a quadratic because its highest degree is 2. You know it's opening downward because of the negative. And the domain then is really, it says state the domain and range once you've graphed it. I think your window is going to be like minus 10 to 10, and then I think probably minus 10 in the y to probably 20 vertically in the y. Your domain is just going to be all real numbers. X is an element of all real numbers. There's no x you can not plug in there. Anything works. But your range, you want to be aware that you're only going to get outputs that are from here on down. So you really want to find that vertex. So if you put in minus b over 2a, which is going to be minus 2.67 over 2 times a negative 0.345, you're going to get the x coordinate right here, and that's going to be an x of approximately negative about 3.869. And then when you plug this back in to x and plug it back in, you're going to get a y value then. That will be your maximum y value ever. And that's going to be f of negative 3.869 is going to give you an approximate value of 18.056 when you round it. Okay, so your range then, you'll say your range is all real numbers except f of x is going to be less than or equal to 18.056. All right, so that's it. Thanks.